Okay. So I hope everybody saw this Piazza message that we'll have a quiz on second. So I will not be there in that entire week, but I can take 2 online classes, and the third one we'll do on a Saturday. Now, I wanted to show you some mathematical things like some how to solve these 1D problems and all. But I think I will keep that for those online classes, because there I will anyway share my screen. Here I have to again ask somebody to take it down, take it up, and all those things. So better I will do it all there. Okay. So let's get started then. So he didn't do this water wipe. Can you just once more call please? Yeah. Okay. So what we will do is that we will continue to do this particle in a box for this week, I think. And so there are 2 general class of problems. One is the problem of bound state, another is the problem of scattering state. So scattering state, so I already discussed that what are the structure of allowed state. So if I give you a general potential like that, then you know this is your x direction, and if this is Vx, and your energy is somewhere here, then there are 3 regions, and I discussed the general structure of the solution. So so classically, you know, so classically this is your allowed, and this is the forbidden region. Because a particle cannot go to a place if it has a energy lower than the potential there. So classically, the particle is not allowed to go there, and so these are all classical. But we saw in quantum there is no such constraint. So this is the turning point. So if you put a particle whose energy is lower than this region, but the potential in this region, but higher in this region, so there will be turning points. Yes. Oh, I wanted to do one water wipe. Yeah. So turning point means the particle will be confined here. Okay. So it will go here, then turn back, like oscillator. So this is actually one of the most peculiar feature of quantum mechanics, that even though some region is classically forbidden, the quantum mechanics allows the particle to be found there. And although exponentially low probability, because we saw this as exponentially decaying function, and this phenomena is called tunneling, and this is at the heart of all the electronics we use today. That is the main phenomena that allows us to do this transistor, diode, everything. What do you mean by that? What do you mean by go through? Yeah, it's an allowed solution. So that means, so the wave function should exist everywhere in a continuous form, right? So, and if there is no infinite wall, so the wave function can exist there. And it has to be continuous with the before turning point, after turning point. So there is always an allowed solution. Now, and then it becomes a question of probability. What is how probability? You can wipe everything. We'll draw it again. वो वाइप कर दीजिए. हाँ नहीं हाँ वाइप कर. Okay. Thank you. I used to go to a drawing school when I was a kid, and there the teachers used to give us chalks after the classes. Okay? And then they said when the room is wiped, the floor is clean. Those days there used to be these red floors. I don't know, nowadays everybody puts tiles or mosaics. But these red brick floors, which is smooth and very nice to draw. So then they used to give us this chalk saying when it is wiped, then draw. Now that time I thought, oh, it feels nice to draw in a clean board, but it annoys the person who cleaned that, right? So that was they knew that, and that's why they said to annoy that person. So this is allowed, this is forbidden, this is the energy. Okay. So the wave function, of course, if you put a ball here, the ball will be stuck. But if you think quantum mechanically, then we learn that the solution will be of this form. How many oscillation, that depends on the energy, right? How many times it is. So let's discuss this a little more, that what are the possibilities. So up to this, everything is fine, right? Yeah. So this phenomena is called tunneling, and this is the core phenomena of all electronics that we use today. Okay, so let's discuss a little more about this structure. Minus ux minus. Okay, so we know this solution will have four kind of properties. Okay, so let's say these are the regions. So this is classically allowed, classically forbidden, classically forbidden, classically allowed. There are two possibilities. One is psi greater than 0 and psi less than 0. Here also psi greater than 0, psi less than 0. So if psi is greater than 0, that means, and you are in a classically allowed region, that means your energy is less than this. So that means, no, energy is higher than this. So that means psi double prime is greater than 0, right? And classically forbidden region, it means psi double prime is greater than 0. Everybody is in the same page with this? Everybody is in the same page with this? Okay. So now what will happen here? So here the psi double prime will be greater than 0 and psi double prime will be less than 0. Okay? That means the what? How am I saying psi is less than 0? It's a wave function. It can be negative, right? Yeah, I'm telling you all the possible solution. So the wave function could be something like this, right? So greater than 0, less than 0. I'm just saying what will be the relation between psi and psi double prime. And that will be entirely determined by Vx minus E, if it is greater or less. And if it is greater than Vx, then it is allowed. If less, it's not allowed. So all I can say is that whether they will be same sign or not, that much. But now you can say a few more things. So if psi is greater than 0 and derivative is also double derivative greater than 0, that means the wave function has this kind of curvature. Similarly, here it must have this curvature. This will have this curvature, and this will have this curvature. Okay. So now let's see how I can fit this consistently with this picture. So let's say I give you two regions. One is classically allowed and classically forbidden. Okay. Which one? Upper right. This. So classically forbidden means energy is less than potential, right? So if psi is greater than 0, then psi double prime should be greater than 0, right? So are you confused about what is classically forbidden? And so nu must be greater than E for classically forbidden. Sorry? Oh, okay, okay. Ah, I get it now. Okay. So this is greater than 0. This is less than 0. Right. Make sense? Yeah, if double derivative has a is greater than 0, it means the function has a minima, right? Then curvature has to be like this, right? Okay. So what more can I say about this problem? So one allowed solution for this. First of all, I know in this part it should be oscillatory, and this part it must be decayed, right? So it must be something like this. So if it is positive, then it must go like this, go towards the origin. If it is negative, it must go towards the origin like this, and here it will decay. Okay. So these are all consistency checks. These are the kind of things you should always carry in your mind to know that whether you can sketch a wave function without solving and all that. Okay. Now, what more can we say? How do we know that how many times how frequently it oscillates, right? What is the frequency? That is given by the energy, because wavelength, more in high energy it is, more wavelengths you can fit in into that region. Okay. So then let me give you one problem and ask you how do you solve this. So let's set up the problem like this. Let's say you have this. Okay. And this is your energy. This is your Vx. This is your how do you draw this? Based on this picture and what we discussed earlier, without solving the problem. Guess, any guess, at least some region. Yeah, but let's start with this. So can you at least sketch the solution uh, in these two regions? No, this one, let me call it 1, 2, 3, 4. So can you say what will be in 1 and 4? Will be decay. Now can you say anything more about that? How the decay is faster in which direction? The decay function is given by difference is more, right? So here it will decay fast, and here it will decay slow, right? So the two regions. Now what about middle? What will happen in the middle? Yeah, so here you will amplitude and frequency. So here the difference is more, right? So here it will be, right? Yeah. There is one more inconsistency here, so I should be careful about that. One, two, three, four. So you can fit in more parts depending on how frequently it is. Actually, no, I should keep not two, only one. The best way to draw this will be coming here and then going like this. Why is that? Because I must fit more frequency here. more periodicity is here compared to this part, because this energy gap, this tells me what is the kappa, right? Kappa is more, means more wavelength should fit there. One more thing I should know, that the amplitude here must be larger than this. So more accurate way to draw this is like this. The amplitude must be larger. This is simply because of the fact, if it has more momentum, it has more speed. If it has more speed, it will spend less time there. That means the amplitude must be lower. Okay. So this is an intuitive reason. You can all solve this, all analytically show this. But I'm just saying you can draw such a wave function just from this without actually solving the problem. Okay. Everybody got this example from all the things we learned? Also, you can check from here that where the wave function is positive, the curvature is this, negative, the curvature is that. Everybody in the same page? Okay, now you can go ahead and solve all the problems in the book. So this is a good exercise to do, although it may not be degree, you might find in books that some potential is given, solve the problem, but try to sketch the solution without actually solving it. There are all kind of problems, like standard problems like this, these, all you can solve. Okay, I will discuss one problem, one of these. I'll discuss this one in detail, full mathematical details. But other rest you can also look it up and try to solve it, at least one of them, and fully rigorously, and sketch all the solutions. Okay. Okay. So let me write down the rules, that all the rules to calculate this wave function. Rules of eigenfunctions. So rule number 1 is bound states. So there will be something called bound states, and they must be normalizable. Bound state means something that vanishes to infinity. Okay, this must be normalizable. Then there will be something called scattering states. That is not zero and not normalizable. What is the example of that? If my energy is this, right? Then the only solution is allowed is this. But double check this, because even though it is allowed, it will have different frequencies at different regions because of its distance from the potential. Okay. So draw that properly. But this is an example of scattering states that goes to infinity, and therefore you cannot normalize it. It's like a free particle. It is like saying if there is some barrier in the way, but if you throw the particle high, then the particle will not see the barrier, right? So this is the example of that. So if you have a particle which is higher energy than the barriers, it will not see the barrier in classical sense, but in quantum sense, what will happen? Its wave functions frequency will still get affected because of the existence of the barrier. Okay? So these are called scattering states. So these will be two types of solution of this problem, depending on what the energy is. Okay? Then, huh? Oh, no, yeah, very good. Yeah. Okay. Now, rule number 3 is there must be continuity in psi and psi prime. That's what we discussed earlier. Psi and psi prime must be continuous. You have to fit all those boundary conditions to solve it. The rule number 4 is classically allowed region will oscillate, will have oscillating solution, and classically forbidden will be exponential. Okay? Exponential decaying, basically, such that it doesn't blow up. Okay? And oscillate means it will have discrete spectra. That you can show from the boundary condition, provided it's not a free particle. Free means completely like that. So it's not a exact correspondence. So discrete and bound. Bound and oscillating solution means it will have discrete spectra. Okay. And forbidden will be exponential, that I already wrote. And the amplitude and oscillation will be less if E minus Vx is high, and vice versa. It's a rule number 4. So rule number 5 is boundary conditions. You have to use the, it's not a rule, but it's a thing to remember that, well, not, let me write this, not boundary condition. You can express this by real functions. So this is something we already discussed, that in principle, you can write down a real function as a wave function, allowed solution of this, all these problems in 1D. Yeah? Although it is not a unique function, because you can always multiply it by arbitrary complex space. Okay? And rule number 6 is bound states follow the node theorem, which means nth eigenstate of this discrete, because this discrete spectrum means they can be labeled by an integer. Right? And if it is labeled by a given integer, that wave function must have that integer minus 1 number of nodes. Okay? That is the node theorem. Okay? It can be real, because always you can multiply by a complex number, right? That's the state. And it's always better to work with real function if you can. So this is the rule of the game. If you have internalized this, you can save your time from reading 2-3 chapters from all the textbooks. Okay? Yeah. Yeah, just look at this, right? Yeah, the wave functions of amplitude and oscillation. The oscillation period. So oscillation means oscillation period. It's the kappa, property of kappa. The kappa will be less. If kappa is less, the oscillation period is less. Wave vector is less. Okay. Wave vector less means wavelength bigger. Sorry? So kappa is wave vector. Wave vector means 1 by wavelength. Wavelength is longer. Right? It's less. Right? I mean, look at here. Okay, let's say. Yeah, it's a period. Yeah. Yeah. So. So okay. So oscillation. So let me call it oscillation wavelength. Wavelength, or in terms of its period, if it is in time domain. Okay? So that will be less. Okay? This is basically simply the idea that you can fit more waves. You can remind yourself that what happened in Bohr's quantization, right? You could fit more wave in the orbit if it is higher momentum, right? And there is another way to think about it, that remember in the particle in a box, this is a mnemonic, okay? Particle in a box had one wavelength for lowest energy, right? But one, no period. Then it had 2 periods. Yeah. Yes.
Then there are lesser number of waves that are
See, what is this quantity E minus Vx? It is this kappa basically, right? So kappa mode means what? It has mode of this. That's what I wrote. Okay. So now let's now that I have laid out all the rules, the general rules of the game, now let's do some rigorous solution. So last time we did one rigorous solution, that is the problem of particle in an infinite well. So what I'll do today is harmonic oscillator, and it's the holy grail of all physics problems, because basically it sometimes says an advanced course in just not condensed matter, also in quantum field theory and everything, is basically defined way to look at harmonic oscillator. Okay, so from now onwards, till the probably as long as you will do physics, you will basically do harmonic oscillator problems in various different format. So it's extremely important problem. It's one of the problem that is well understood, and a large number of problems are modeled around our understanding of this. So let's go through this. And so I will do now three, in 1D, I think I'll do 2-3 problems. So let me list the problems first, then I'll tell you. This general rule is very important, and it's important that you solve some problems from books to properly internalize this and such that it is handy to you. And there is I was talking to somebody that what is the difference between education at our time and your time? Generally, the students know more. Like at your age, I knew nothing. Like at least none of I had nowhere close to what I'm teaching. Like my understanding level was very poor. But you guys understand far better than me at this age, at your age. But you have very poor retention, which means whatever you understand, you forget quickly because you don't practice. So you spend very little time with the material. Okay, this is the problem. This is generally true. I have seen that. So spend some time. So it's not enough for you to understand. You have to keep it inside yourself. And as soon as the semester gets over, everything gets flushed out of your brain if you have not solved problem. This is the main thing. I can assure you that. There's no point of listening if you are not solving the problems. And only the part you remember after many years is this, what you have solved. Okay. So now I will discuss, okay, let me first list for all the problems. So one is infinite. So as I said that there are 5 types of problems. So infinite square will. So one type is nicely behaving function but abruptly stopping somewhere. It's going to infinity at infinity. So infinite square well is one such problem. Then simple harmonic oscillator is also like that. A nicely behaving function but goes to infinity at infinity. This also goes to infinity at infinity but abruptly, not like smoothly. And third problem is finite square well. So this problem, notice there is no question of scattering state, right? You can never go to infinity, right? So there is no question of a solution that is going to infinity. That it has to be confined. It has to be bound state. So that's why all the solutions were bound, oscillatory, and discrete. Same will happen here, but little differently because it doesn't go to abruptly goes to infinity. The finite square well will not be like that. So this means it has a finite depth. So this is infinite one. So this is a finite well, which means you can have energy above the and below the depth, and they will have different properties. So we'll discuss that next. You already know how to sketch this. We just discussed, but we'll do it rigorously. And this is basically the problem in whole physics. This is the problem which appear in many formats. Like starting from anything you do on a lab in electronics, let's say. What you have a chip with different gate voltage and potential, and electron is passing through that. What you do in a collider, it's a region of interaction. So you shoot a particle, in some region of interaction, something happens. It comes out, you capture that, right? It's basically a problem of a 3D potential where you throw a particle and catch it somewhere and see what's the wave function and properties change it. The Rutherford gold plate experiment, right? You have studied that. What was it? A Coulomb field of a nucleus where you shoot a particle, it goes and comes out, right? Same problem in different format. Okay? So we will learn these problems in full glory in quantum mechanics 2, in a chapter called scattering. Here we'll only learn the 1D version of this problem. All experiments are one or the other form of scattering. X-ray diffraction, collider experiments that they do in CERN, or neutron diffraction experiment in that we do to understand the spin configuration of a system, etc. Almost all the experiments are worked on the other form of scattering. And transport is also a form of scattering, electron passing through a wire. Right? So this is an extremely important problem. And the other kind of experiment we do is spectroscopy, right? The whole atomic physics is spectroscopy, spectral lines. And what's the story of spectral lines? You have some bound state, either this or this, electron jumping from here to here, releasing some photon, some electromagnetic wave, which you analyze. Right? So these problems are basically, although we will just discuss the problem in a textbook manner, but they are the most important problem. From now onwards, all the advanced courses you will learn, as I told you also earlier before. So these are the 5 fundamental subjects: classical mechanics, electrodynamics, stat mech, and quantum mechanics, and math methods, which is a toolbox for all this. All the courses you will learn is basically application of all those problems you learned in all these places. Atomic, molecular, solid state, particle physics. Every courses you learn from here are basically this problem in more and more complicated and refined version. So pay a lot of attention and make sure you fully internalize everything. Okay, so these are the 3 problems mainly I will discuss. And then there are, all the problems are basically some variants of this. Okay, so in book you will find some delta function potential. So, so let me call it miscellaneous. I forgot the spelling. Okay, so something, some delta function potential, or some barrier, or half harmonic oscillator, a harmonic oscillator where you put a wall, or any of this problem you can distort it, right? You can have a particle in a box, you can put a barrier in the middle, etc. Okay? I will discuss some of the variants, but more or less it's not, of course, I cannot keep doing all these problems throughout the course, but I will give you an idea that how to solve this kind of problem. And this problem I'll do it in 2 different ways. One is a differential equation way. There is algebraic way. So this algebraic way is very profound. It will lead to something called second quantization, and everything will be done in quantum mechanics too. So this is the landscape of the topics and their importance, which we'll learn in this week and maybe a little bit next week. And then we will, this is all 1D. Okay? Then we'll go to the 2D and 3D version of these problems. So 2D, I will spend 1 day, because 2D, one important thing will appear called degeneracy, which was not there in 1D. And I will mainly talk about this problem and the squared well, and give an idea about what happens. And 3D we will do mainly Coulomb introduction. Also a bit of SHO and squared well we will discuss. And that is the subsequent part of this course. In 1D, actually, you can also discuss a Coulomb-like potential, but that is really tricky. So, did you understand that? Did you learn in ED course that if you think of electromagnetic potential in 2D, it becomes logarithmic, and in 1D, it becomes like a delta function? Okay, maybe think about this, that why inverse square? Out of all these possibilities in the world, why inverse square? What does it accomplish? So think about this. So it, Coulomb force, gravitational force. So my statement is, will it be inverse square in 2D? And by 2D, I mean pure 2D. I am not saying about 2D in a 3D world. If the universe is 2D, if you think of a completely 2D system, which has where, like, you might think of, okay, I can have a point charge here, but the field lines can escape, can be in 3D. That let's say I do not allow that. It must live completely in 2D. So think about this, that why inverse square? Why do you need inverse square? So it's a property of dimension. It turns out in 2D you don't need inverse square, you need logarithmic to satisfy the same properties. Okay. Anyways, so we will do only Coulomb, because that's what almost all systems are. So to make a 2D system, you need to engineer a lot of things. which is there, which happens in lab, but naturally what we do is 3D. Okay. Okay, so let's start with this. So we discussed already this. We discussed this schematically, but let's now do this problem. So this is a natural continuation of this problem. So let's do simple harmonic oscillator. Actually, let me wipe the board and start from here because this will be a little rigorous. You learned of series solution of differential equation, right? Hermite polynomial, Legendre polynomial. Oh, then it will be very easy for me. Huh? You know the spirit of these polynomial solutions. What did you learn? Legendre. That's good enough. Yeah. Any one method is, if you know the idea, then it is fine. I mean, there are infinitely many things, right? How many you will learn? You will learn it when it requires it. Okay. So let's start by, oh, one more thing I missed. Did somebody try to prove this point I mentioned last time? That yeah, so in a 1D problem, the allowed energies must be always greater than V minimum. Did anybody try to prove this? It's there in Griffith, example 2.2. And also bound state. That I forgot. Okay, anybody try this? Because if you remember, I started this problem by saying E is greater than 0. Then I tried to find out the solution because the floor of this function is right there. Nobody even opened the book or turned the pages. Okay. I am not giving you the solution. Look it up. But you have to use this picture I have drawn. Right? When is psi greater than 0 and psi double prime? So if this is true, right? So then what was this? Psi double prime mu minus E psi. Okay. So the idea is this: if this is true, then they have to have opposite curvature. So if they have opposite curvature, then it must look like this. The function must look like this. And if it looks like this, it cannot be normalized. Okay? So if you want to normalize a solution, which you have to because it's a bound state, then you cannot allow such a solution which goes below V minimum. Now, this is a pure mathematical property, but it also has physical consequence. Because if you if you allow a system to go have arbitrarily low energy without a minimum, there exists no minimum, then the system will never be stable because such a system will always try to go lower and lower in energy. There are examples like that, not physical examples, but so yeah, so this is the point. And and this has a very interesting connection with the point when, if you remember, we stated earlier that we cannot take time as an operator, because if you take time as an operator, you have to allow a minus infinity to plus infinity spectrum for energy, which is not allowed at least in 1D problems, 1D bound states. But it turns out such a thing can be allowed in many body quantum mechanics. And there you can technically allow time as an operator, but that leads to other kind of problems. Okay? That's why instead of making time an operator, you make position also a variable, a parameter of the theory. And that is the starting point of quantum field theory. Okay. So let me go over harmonic oscillator. It is the most standard problem. Everybody is in the same page so far? Okay. So the problem is following. You have a potential like this, which you have done, of course. So Vx is half m omega squared x squared. Now you might think that this is a very special problem, but it turns out actually it is not so special, because you can have an arbitrary shape potential where with a minima, and you can always think that if I am close enough to this minima, okay, so Vx, I can expand it as Vx naught, Taylor expansion, x minus x naught, V prime naught plus x minus x naught square, the double prime x naught, and so on. Now, if generally, if it is a minima, okay, if it is a minima, so first derivative will vanish. So that means the Vx will be approximately Vx naught plus x minus x naught square, V double prime x naught plus order of higher terms. Right? So that means any problem that has a well-behaved function with a minima, you can approximate that as a oscillator-like potential near the minima. And it turns out there are, at least in many body physics and condensed matter physics, most problem falls in either this category or another category, which is linear potential. And they have very interesting differences. When the other category is this, let's say you have a potential like this, and you are interested in finding the property near this line. So this is you can approximate as a linear function. And it turns out when it is a linear function, it has a very interesting difference from these quadratic functions, these kind of squares. And that leads to two very different distinguishable class of behaviors. And one you have to deal with Dirac equation and all that, another is Schrodinger equation. But without entering into all that details, let's just tell you, this problem is more general than an idealized harmonic oscillator. This problem is relevant to many other scenarios when there is you're trying to know the low energy physics near the minima of a potential. Okay, and so now let's take the Schrodinger equation. And as usual, we'll first clean the equation to make it dimension free. So the rule is, so as we always did, that we want to clean this part, such that there is no, this is also energy times psi, this is also energy times psi. So I want to make it energy dimension free. So the way to do it is by noting, and the problem is this guy, right? Because this is already, well, also this guy. So this must be such that minus h cut square by 2m with a dimension of length square must be equal to half m omega square, some dimension of length. So we have to set some length dimension here. Right? So first let's do that. It's the length is creating a problem, because here the length is denominator, here it is numerator. So let's set a new definition of length called u. So a multiplied by u, where a is a quantity of dimension length, and u is dimension 3 number that represents length. So now you can set these to be equal, because x square is in denominator. So you can set the length in a way such that they match. That's the game. And that is solution of this equation. Okay. So if I do that, then h cut square by twice m omega square becomes h cut omega by 2. So now you get this whole thing manifest here energy dimension, which is h cut omega. And this is half m omega square. A square is also, just plug in this, it is also h cut omega by 2. So both of these are now manifest the energy invariant if we work in a unit of u, if you work in the length coordinate u. So that means if I plug that in, your this equation will become minus half h cut omega d2 psi du2 plus h cut omega by 2 u square psi equal to e psi, which is basically d2 psi du2, take the u square this side and h cut omega also this side, you get u square minus e where e is 2e by h square. Okay, what did I do? I just took that 2 here divided by h cut omega, called it epsilon and cleaned up the equation. Just the same exercise which we did before. Okay? So this is a unit free equation of differential of quantum harmonic oscillator. Okay? So now I will try to solve it and ask the question that for what E we have a solution, a normalizable solution, and so on. And of course, we can expect there is also no scattering state because the wave function goes to infinity. So whatever energy you pick, it will be somewhere here or here, it will cut through it. You cannot ever go above the whole potential energy. Okay? All will be bound state. Okay, everybody in the same page so far? Good. So now I will start thinking about the solution. No, I just separate x into two parts. One is a constant that carries the dimension full, another is the number. Right? I can always do that for any quantity. I separate a constant and a number. So the constant here is this. It is pre-decided by the natural constant h bar and the properties of the problem that is given at the beginning. No, these two has to. Oh, how are you getting this? I didn't get your question. Yeah, so what is the goal here? Like that's what we have been, this is the third time we are doing this. That our goal is to manifest that this, both of this side is basically energy times psi. And the problem here is that here there is a common quantity. That common quantity is x. Once it appears in numerator, once at denominator. So I want to set these two quantities to be equal and equal to energy. Okay? So while doing that, then I have to fix the A, which is in a way such that that happens. So that is what I did here. Okay? Are you getting the point? That's what we did also in other problem, but other problem didn't have this issue because there was no x hanging, general x hanging. This is exactly the same exercise which we did here. But this was general here. It was just a quantity with energy already dimension. But now it's not just energy. It has its own structure. So that's why I have to arrive at this different dimension of length. Right? Makes sense or not comfortable? Where? This. What was this? No, this is a square. Right? See, this is same exercise as this, except this is not new anymore. It has its length inside it. So I have to take account of that. And that is why I am specifically fixing this A in a way such that it comes in a dimension free form like this. So now I have a dimension free. So there this problem didn't happen because this is basically d2 psi dx2. It actually carries the length unit. But here I am wiping that length unit inside this. That's why I'm setting thing in that way. Sorry? How it is this? I will do a little bit of algebra. So A is plug this in here, right? Yeah. I mean, you have to something you have to do at home, right? The point of this exercise is to make the whole thing dimension free. If you think of that, then it is very simple. That however way you want to do, all the quantity in this equation has no dimension. And it is just psi equal to psi, whatever the dimension psi is. And you know the psi dimension is basically, so 1 by root L, right? It has to be 1 by root L. Okay. So now I want to see the solution of this equation. So again, let's do some asymptotic solution. So I want to learn first, I want to know as much as possible about the character of the solution, because it's a non-trivial equation to solve. This has a second derivative here. Here you have a u squared, and then there is a, so there are two types of function. Like one is a u squared times this function, and there is no power of u, just a constant times the function. So it is a inhomogeneous form. So it requires some non-trivial attempt to solve this. You have learned probably, did you learn this form of equation or some other form of equation in series solution? Okay. Okay, so that's also fine. Okay, but Laplacian doesn't have any inhomogeneity, right? So, okay, so this one has inhomogeneity. So let's see how to deal with that. So let's see the asymptotes. Asymptotes means u going to infinity. So what will happen in u going to infinity? The u is much bigger than the epsilon. So the solution will be approximately u square. The equation will become this, approximately u square psi. Now, of course, what you can guess from here, it cannot be a polynomial, because if so, we want to find the psi, so it can't be a polynomial. Why? Because a polynomials, if you take two derivative, you cannot have u square times that polynomial, right? So it cannot be a polynomial. That's ruled out. So it has to be an exponential. Has to be some exponential. Now, exponential doesn't always mean decaying. It could be a Gaussian form. So it has to be an exponential, and it can accommodate a polynomial as p factor. So only if it is an exponential form, then it can allow a solution of this kind, or it is at least an exponential times a polynomial. That's also an allowed form. So let's try to see what kind of structure I can guess. Polynomial mean what? Here it is u, there is no x anymore. So it cannot be of any form of this form. But it can be this times some exp, like minus some u fu. It could be u square, u cube, anything, u anything. So at least you need this much. That's our guess. So then come up with the simplest trial function which satisfy these two things. So the simplest trial function is of this form. Now you might wonder that why did I choose this, not some other power of 1 like u. That's because I know it's a bound state, so I don't want a decaying or growing solution at least. Okay, and it's also this is not yet coming here, but we'll see that we earlier proved that if the wave function is symmetric, right, bx is equal to minus bx, then the solution will be either purely odd or purely even. So this is why my first guess is this, that I want it to be bound state. So let's write down the possible two possible cases. Also, again, alpha could be anything, plus, minus, anything. Okay? This is a guess solution. So then if I write a general solution, so this is approximate form. Okay? So the general solution must be of this form. That is satisfying this approximate equation, which is a u going to infinity limit of that equation. So it must be of the form e to the power. Now notice what more can I say? If I plug this into this, okay, then I get d2 psi du2 alpha square u square psi u. Okay? So check this. If you take two derivatives, alpha square will come here. Okay? But you started with something that didn't have alpha. So that means the alpha square must be equal to 1. So alpha must be equal to plus minus 1. So then the psi u must be a e to the power a u to the power k e to the power minus u square by 2 plus b u to the power k u square by 2. Okay. This must be the structure of the solution. Okay. Now, if u goes to infinity, okay, if u goes to infinity, then this part will diverge. So I don't want this part either. So what I want is a solution that is approximately of this form. Okay. Remember, this is square. So square will always go to infinity if you go to infinity because it's a growing part. Okay. Everybody in the same page so far? That why did I land on this? It's a polynomial times an exponential, which must be of this form. So this is my best guess so far. Now notice that this guess is little. So you might be thinking that there is nothing special here. Why? Because I can always generally say, so it's a polynomial function. That point is very important. Otherwise, I can always do this, right? I can do some psi u e to the power u square by 2 times e to the power minus u square by 2. That is hu e to the power minus u square. So why did I work so hard, right? I worked so hard to make sure this part is not this. It is a polynomial. This must be a polynomial. Now I will show that it must be a polynomial of finite order. It cannot be infinite polynomial. Okay. So let's, time is almost up, actually up. So let's just give you an idea about how to proceed from here and then take it over from next time. Okay. Everybody is clear about up to this, right? Avoiding eye contacts, everyone. So next what I want is that, so we figured that the solution in the asymptotic limit must be of this form. So now I want to find out what is this hu. Okay. So what do you do for that? Now it is coming to the domain of your series solution. What do you do from here? If you have it, you start with the trial solution, right? Completely like washed out of your brain because of not solving problems. So this is everything. This is exactly what will happen to the entire course. Right, the day course is over, it will decay. Your memory will decay like an exponential function with infinite coefficient. Okay, everything will be washed out in a moment. This is what I'm telling you. This is the difference between people who in my time, at least. This was partly not entirely your fault because in my BSc, the coursework the system was there was 2 year of course, then one exam, which is a high pressure exam because 2 year of one exam. It was like a very high pressure. If you do bad, it's doomed. Like no semester, no test, nothing. And then 1 year, another exam, right? So what happened that we really learned very in a relaxed manner, everything, all the subjects we wanted to learn. And the subjects we didn't like that we studied a month before the exam. But that allowed us to really retain whatever we learned, it stayed with us. But for you, I also had a big trouble when first time I went to masters and went to semester. First semester was disaster for me. Then I adjusted to the system. And the adjustment is that you have to study every day. There is no room of taking a little time, thinking and absorbing it. Okay, so this is the secret of any semester system. You have to, at least for subjects like this, there are some subjects which you can probably sit one day and use your common sense and get the picture. Subjects like these it's like math in school, right? If you don't practice math every day, it is a disaster. Like I think in my 9th standard, I got 36 out of 100 in math. And the reason was I was playing whole day and didn't study. All other subjects were fine. I didn't study any subject. It didn't happen in any subject, only happened in math. So this is like that. This is like math. If you don't practice, this is what will happen. Okay, so the strategy is following. You have to plug this solution into this. Very simple strategy. And then you get a differential equation for H. So do this. So this is where I leave. So if you plug this into this, you will get this equation. Okay. And revise your series solution to see that how do you solve this H using a series solution. So HU will be U to the power J plus alpha 1 U to the power J minus 1 and so on. So use your series solution, revise your series solution and figure out that how do you solve this. So notice that this has two parts. One part is the H, another is the polynomial. I want to find the polynomial because that is the whole game of series solution. The U square part is it's an infinite series. And in order to do that, you have to plug this in here and you have to convince yourself that the U to the power minus U square part doesn't contribute because there is a double derivative here and U square here. It will just fall off and you will get a differential equation of H, which is the inhomogeneous part. And then look up in your series solution textbooks that how do you solve this kind of equation. So that's where we will take it. We'll take it from there, and we'll learn two methods of solving this problem. One is this series method, and another is some algebraic. Okay? So that is all. Okay. So do problems, as I said many times. If you are not doing problems, it's total waste of time. What did you think? Where are you coming from? Okay, but he said this legendary polynomial. How else did you learn? Huh? This Laplace equation and all for defined potentials, right? Okay. Are you reading from Jackson or some other book? But I thought Jackson has a very good discussion on the origin of how do you think about this solution and all. But did you learn series in math methods? Just series, infinite series, convergence criteria. Okay, I have to see then your syllabus and all because I'm thinking because last year somehow people knew that. What happened? Oh, again the same problem. What about Fourier series? Now you know. Now you know about Fourier series, right? Okay.
that day when you asked,
Yeah, yeah, I also talked to her, and I think she says it is true. But this is a differential equation that is expected to have a polynomial solution. So that is the whole point. Okay, so which book are you following in math methods? Riley? Huh? Afghan? Oh, no, one book. Okay. That's generally always true, but this is my general advice to follow one or two books because it's difficult for a student to look at many books. This is also in quantum mechanics. You will find I use many books. Like I gave you all the list of books, but every book has different notation. It's very difficult to follow. So follow one or two books. When those books are priority-wise, it's Sakurai and Griffith and Shankar. But you can follow any book you like. This is Griffith. Griffith is very nice for this. It's there in any book, but Griffith is. Yeah, Griffith formalism is a little too over diluted. For that, I think if you want to get the full picture, the best book is Dirac. But Dirac is hard to read. So the comfortable middle ground is Sakurai. So Sakurai's first chapter or Shankar's some chapter, I don't remember which chapter is that. Yeah, so that you should internalize. Yeah, it's Sakurai has everything, but it's a little complex. That's the problem. But it's still okay. I mean, it has everything. That's why you need the help from classes, not a book for self-study. So if you are taking understanding things from class and reading it at home, it will be fine. Sorry. You finished that? Oh, very good. So now I think I can talk about this. How it comes in. I think. Yeah, okay, I'll see. But let's at least finish these parts. So these parts are usually taught in great detail in other courses like chemistry and all. But this part is the easy part. It is all about just solving the problem. Formalism you already learned.